This is G481 Homework Booklet, question 29. We see a wooden block motionless on an inclined ramp. This suggests that it is an equilibrium situation. First question is asking us to add the normal contact force and the frictional force to the diagram. In physics, the word normal means perpendicular or at right angles to. So here is the normal contact force at right angles to the surface of the ramp. And friction is acting up the ramp so that it is opposing any motion if it were to slide downwards. Next we have to write an equation to relate this friction force to the weight and the angle. So we need to look at the situation, remember it's in equilibrium, and establish that the component of the weight that's acting down the slope must be balancing the friction force that is acting up the slope. We can ignore the normal reaction because that's perpendicular, so will have no effect in this direction. Two ways to do this, but both of them depend on realizing that this angle here, the angle between the weight and the direction perpendicular to the slope, is theta and equal to the original angle given in the diagram. So in this triangle, this is theta, this is 90, this must be 90 minus theta, so this angle is theta. Having realised this, you may be confident enough just to look at the situation visually and to realise that when you swing through an angle from a resultant force to its component, you can use cos, and when you move in the other direction from the angle given, you use the term sine. So that can give you F equals W sine theta. If you don't like to use that visual technique, then you need to construct the vector triangle, showing the two components that add up to the weight. Then you can just use trig in that triangle to get the same expression. So the component of the weight down the slope is equal to the friction force. Moving on to part B of the question, we have another equilibrium situation, but this time we're going to be using moments to solve the problem. The text just reinforces the information given in the diagram. So we have the weight of the cupboard acting downwards, 200 newtons, at a distance of 12 centimetres from the pivot. We also have a screw that's holding the cupboard to the wall, and this is a distance of 75 centimetres from the pivot. And we have an unknown force here that's holding the cupboard to the wall by the screw. So first part of the question is asking us to state the principle of moments. So for an object to be in equilibrium, the sum of the clockwise moments about a point must equal the sum of the anti-clockwise moments about the same point. The word clockwise was used to judge the spelling mark, and the other points underlined in green are what make it a good enough answer to be worthy of 2 marks. Next we have a calculation, so we're going to use the principle of moments to find the unknown force F. The clockwise moment, if we look back at the diagram, was 200 newtons acting at a distance of 12 centimetres. So we multiply these two values to get the clockwise moment. Anti-clockwise, we have the unknown force multiplied by this distance of 75 centimetres. Always check that the distances you are using are perpendicular between the line of action of a force and a pivot. So fairly straightforward substitution into the moments equation. The clockwise moment equals the anti-clockwise moment. Only one moment in each direction in this particular example. Rearranging the equation then allows us to give an answer of 32 newtons. Notice I chose to work in centimetres here, which is absolutely fine. It's important to be consistent on both sides of the equation, and to remember that if you were asked to find a moment, you must match your units with the units you've used in the calculation. So, for example, if you were using these two values and quoting a moment, you would actually be quoting it in Newton centimetres. Moving on then, the final part of the question asks us to think about pressure. So we have pressure is force divided by area. This was the force exerted by the screw, 32 newtons, quite simply divided by the cross-sectional area of the screw head. Again, be careful with units. Here you're given the units required in the answer, pascals. Pascals are equivalent to newtons per metre squared, so you have to check that this area was in fact given in metres squared and the force in newtons. If it wasn't, you would have to deal with a conversion first. And now to look at the overall situation and explain how your answer for the pressure would change if the same screw was secured closer to A. This is the equation that you had for the moments. You had the unknown force originally times a distance of 75 equal to the clockwise moment, the weight of the cupboard, times the distance to the pivot. So we go right back to that point and see how each of the variables is affected. If we decrease this distance, but this moment must remain the same, then we would need to increase the force in order to get the required anti-clockwise moment to keep everything in equilibrium. If we increase this force, we can follow the logic to the pressure calculation, and increasing this force will increase the pressure. It is very good to show that you are using equations in an answer like this, but remember to back your answer up with a written statement concluding what you have worked out.